University. So I just graduated this year. I'm waiting for the ceremony, and I came here with a team of my friends who came to support me with my project. So this is more like a team thing that I made up, and I'm the engineer behind the project that I came with. So I'm here presenting a project that is known as microbial fuel cell technology, which uses wastewater to generate electricity. So, just a quick background. From the time I started researching on this technology, I found that wastewater is actually the water that we deposit from various uses, from our uses, different things that we use. And for the government to treat this wastewater, they use the council. So the wastewater treatment plants are the ones that are used to treat this wastewater. But looking at the wastewater treatment plants, they are a vital industry. They use large amounts of electricity in order for them to actually treat the wastewater. But I came up with this technology to find that the wastewater treatment plants, they can actually be used to generate 10 times more electricity than the amount of energy that they are used to treat this wastewater. So this microbial fuel cell technology is the technology that we can actually use to treat the wastewater and also generate electricity for use. So for a definition, microbial fuel cells is a bioelectrochemical device that generates electric current by oxidizing organic matter that is found in the wastewater using bacteria as a catalyst. So it's consisted of two things. It consists of an anode and a cathode. So an anode is where the microbes are consisted of. So they break down the organic matter and then they release the electrons. The electrons will have to flow through a complete circuit and then they go through the cathode to go and meet with oxygen as a terminal electron acceptor. So from the research, I found that deep in the sewers in the wastewater treatment plants, these microbes are billions of them, and in the environment, they are able to break down organic matter and release the electrons to the environment so that they exchange with energy. So they release the electrons in exchange for their own energy with oxygen. And they are also able to oxidize metals such as iron, even radioactive substances. But in a microbial fuel cell, this technology is able to capture those electrons as they oxidize the organic matter, even the metals, and then they generate the electric energy that we can actually use. And this kind of energy can actually be used for different kinds of things. So there I have an MFC, which consists of the anode and the cathode. So in that MFC, what is happening is a bioelectrochemical reaction on the anode, and then as the electrons are produced, they move towards the complete circuit and go to the cathode, and then there's also a production of hydrogen in smaller amounts. So in the wastewater treatment plants, in the entire process, the most important part for us to deviate from wastewater to energy generation is at the secondary clarifier. That is the secondary stage where anaerobic digestion is used to break down the organic matter. So these microbes are also found in the secondary clarifier to break down those electrons and then generate the electricity. So that is where we can place this kind of technology in order for us to produce a different kind of energy generation system. So the problem statement I came up with was that the hydroelectricity power reservoir is a renewable source of energy. Yet this reservoir also gets to deplete in terms of, because of droughts and also due to high energy demands. So we end up having power shortages from our hydroelectricity and also dependence on fossil fuels, which are non-renewable and also increasing carbon emissions. So in order for us to reduce on that, we try to find a renewable source of energy, and that's where the wastewater treatment plants come in. So in order for us to also find a sustainable way of producing power. So my main objective was to design and construct a pilot scale model of a battery consisting of MFCs that would produce a continuous amount of energy that would be used for electrical devices, and also to measure the amount of time for the cells to work, which would be sustainable and also reduce on costs. And specific objectives were to generate the voltage at least 12 volts from each cell, and also to achieve a current of at least 3,000 milliamps to apply to the load and the current flow for a period of time. So for my research, I actually completed about 6 years of doing my research for microbial fuel cells before I even went to Copperbelt University. So when I started doing that research, I never knew it would actually work, but after some time, I started researching on the internet, and then I found that Pennsylvania University actually came up with various models which were complex and which were also producing amounts of electricity from wastewater. But the thing that I found was the kind of technology that they were using was similar to mine. However, it was very expensive. So I started doing my research, and then I found a better way of doing it, and I found simple ways of making that model. So I came up with a prototype, and from that prototype, I used two glasses. So two glasses as chambers, and aluminum sheet as my anode, and copper as cathode, and kitchen wastewater as the electrolyte, and also used a soap bridge in order for me to make a complete circuit. And I got this idea from a galvanic cell, which is used to generate electric current from a spontaneous generation and used to measure electricity from different electrolytes, like sodium chloride. So there is my prototype. I came up with that prototype, and then I connected to a resistor for an amount of 70 days. So for my results, I came up with a total energy output. From the 5 cells, I came up with 2.9 volts and a current of 140 milliamps, respectively. And I started measuring the amount of time it would take for the voltage to actually reduce to a point where I couldn't actually use the fuel cells. So after 70 days, the fuel cells actually degraded the voltage up to 2.3 volts. 2.3 volts from standard batteries could actually be used, but looking at the current that I produced was very minimal. 140 milliamps was very minimal, so it was very difficult for the cells to actually use that voltage. So I needed to optimize in terms of the current output. So from my results, about the 70 days, I came up with a graph. Looking at the 5 cells, they were having different reactions inside, and the voltage outputs were varying, having a similar factor by 0.1 of decrease in voltage, but the voltages were differing in each cell depending on the chemical reactions and the temperature of the cells that were placed in one position. So I came up with different variables of the voltage output at the end of the 70 days. So from my expected outputs, I discovered that these microbial fuel cells actually have the potential to treat the wastewater and generate power. And also they have a potential to form a decentralized system of power generation in the entire country. So we could use districts instead of having only one power plant. In order for us to reduce the power shortages, we form a decentralized system of power generation where each district gets to have its own electric power station, and so that we can actually produce that electricity for at least houses, and also some businesses and houses can actually use that that electricity, and then industries can actually use the electricity from the hydroelectricity. And they also have a potential to produce cheap electricity once they are used, once reduced on the cost of generation and also the cost of establishing companies. So it has also released greenhouse gas emissions during power generation because it only uses bacteria that breaks down waste. So there's no any emission. So internal resistances were coming from my technology as a result of the distance between electrodes, and also the materials that I used. I came to find that I needed to optimize it in terms of changing materials, looking at the bacteria. So the number of bacteria will have to make sure that they are in a good environment in order for them to actually produce the electrons, because they don't produce electrons in any environment. So they had to have a maintained environment, and also to make sure that the environments are sterile. So they did not need pure cultures. So I failed to have a pure culture. Reason being, the technology that I was using to separate the bacteria was limited. So I needed a technology that would help me to separate the pure cultures and also use them. So I had those kinds of challenges. So from those challenges, I came up with a better solution that we also need to increase on. We need to invest so much in starting up with this technology. However, it is a very good technology to use. So from the recommendations, I recommend that we take advantage of this novel technology where we can use wastewater treatment to produce electricity. And also, microbial fuel cell technology is not only limited to wastewater treatment plants. It can also be used to install small batteries in specific houses. Each house can have its own microbial fuel cells. They can be used as storages for energy, and this can be an alternative in case we have problems with power, we have shortages or load shedding. This can be an alternative. And also to consider a decentralized system of power generation to reduce the cost of the distance from the power lines and also from the consumption points. And for my future work, I intend to go with a pilot scale microbial fuel cell, which uses wastewater as an electrolyte to also produce the 12 volts. So my main objective is my future work. So I intend to produce at least 36 watts per meter cubed, which can be used to establish an amount of time to drive electric devices in households such as light bulbs, TVs, and other electric appliances. Thank you.